Something is glowing on Neptune, and it should not be there. In March 2025, the James Webb Space Telescope captured light shimmering across Neptune's atmosphere, auroras, but not at the poles like you would expect on Earth. These lights were at the mid-latitudes, across the middle of the planet, in places where, according to everything we know, they have no business being. At the same time, Webb detected a temperature crash in Neptune's upper atmosphere so dramatic that scientists are still trying to figure out what caused it. These two things, the impossible lights and the vanishing heat, happened together, and no one knows why. That is what we are getting into today. This is Neptune, the last planet, the most mysterious world in our solar system, and the one that just gave us more questions than answers. Subscribe and stick with me. This one goes all the way to the edge of everything we know. There's a planet sitting at the very edge of our solar system. It is so far away that the sun, the thing that lights up your entire sky from horizon to horizon, would look from there like nothing more than a very bright star. A pinprick of light, barely enough to read by. This planet is so cold that its average atmospheric temperature sits at minus 201 degrees Celsius. Its winds are the fastest ever recorded on any planet in the known solar system. It has storms that are larger than the entire Earth. And yet, and this is the part that should make you stop, we have only ever visited it once. One spacecraft in 1989 flew past it for 3 days. Everything else we know has come from telescopes, from a distance. And for decades, that was enough. We thought we had a reasonable picture of Neptune. We knew it was cold, distant, violent, and beautiful. But then, in March of 2025, the James Webb Space Telescope looked at Neptune, and what it found left scientists with more questions than they started with. A temperature crash that nobody predicted, lights glowing in places they should not exist, and a planet that, after all this time, is still refusing to be fully understood. This is the story of Neptune, and it is stranger than most people realize. Let us go back to the beginning, because Neptune's story does not start with a telescope. It does not start with someone scanning the sky and spotting a new light. Neptune's story starts with mathematics, with a man sitting at a desk with a pen and paper doing calculations, and that is what makes it unlike any other planet ever discovered. By the 1840s, astronomers had been carefully watching Uranus, the seventh planet, for decades. They were mapping its orbit, checking its position against predictions based on Newtonian physics, making sure everything added up. And for a while it did, but over time, something started to look wrong. Uranus was drifting, not by much, not enough to see with your naked eye, but enough for the mathematics to show that something was pulling on it, something beyond it, something with enough gravitational weight to nudge the seventh planet slightly off the course it was supposed to follow. A French mathematician named Urbain Le Verrier looked at this problem. He sat with the numbers and the calculations, and eventually reached a conclusion. There had to be another planet out there, one we had never seen. And not only that, he predicted almost exactly where in the sky it would be sitting. On September 23rd, 1846, a German astronomer named Johann Galle took that prediction and pointed a telescope at that specific patch of sky. Within 1 hour, he had found Neptune, a planet calculated into existence before anyone had ever looked at it. Nothing quite like that had ever happened before, and nothing quite like it has happened since. But finding it was only the beginning of the problem. Because Neptune is not a place that is easy to study. It orbits the sun at a distance of roughly 5 billion kilometers. That is 30 times the distance between the Earth and the sun. When you try to look at it through a telescope from Earth, you're staring at a tiny blue smudge. The detail is almost entirely hidden by distance. You cannot see its surface. You cannot see its moons clearly. You cannot see its rings. You can barely even confirm the color. And sending a spacecraft there is not straightforward either. With the technology we have, a probe needs somewhere around 12 to 13 years just to make the journey. 12 to 13 years of travel through empty space, aimed at a moving target billions of kilometers away. The level of calculation and patience required is almost difficult to comprehend. There was, however, a narrow opportunity. Once every 175 years, the outer planets align in a way that allows a spacecraft to use each planet's gravity in sequence, a slingshot effect, dramatically cutting down the travel time. That alignment happened in the 1970s and 1980s. NASA recognized it as a once-in-several-lifetimes window and launched Voyager 2 in 1977. The probe visited Jupiter first, then Saturn, then Uranus, using each planet's gravity to accelerate itself toward the next. And on August 25th, 1989, 12 years after launch, Voyager 2 finally reached Neptune. It passed within just 5,000 kilometers of the planet's north pole, closer than any flyby of any planet during the entire mission. And for a few days, the data came pouring in. What scientists saw when they finally got a clear picture of Neptune was stunning. The planet was a deep, vivid blue, richer and more saturated than Uranus, which sits at a similar distance from the Sun and has a very similar composition. The difference comes down to methane. Neptune's atmosphere is made up of about 80% hydrogen. Helium makes up most of the rest. But it is the methane, sitting at roughly 1 to 2%, that absorbs red wavelengths of sunlight and scatters blue light back outward. The result is a planet that glows like a deep ocean from space. But the atmosphere is not sitting still. It is one of the most violent environments in the known solar system. Voyager 2 measured wind speeds that stunned the scientists receiving the data. At the equator, winds were blowing at roughly 2,100 kilometers per hour. That is close to the speed of sound. These are the strongest winds ever recorded on any planet. And what makes them stranger still is that the majority of these winds travel in the opposite direction to the planet's own rotation. Neptune spins one way, and its atmosphere tears across it in the other direction. Even now, the reasons for this are still not fully understood. During the flyby, Voyager 2 also spotted a massive dark oval storm spinning counterclockwise through Neptune's southern hemisphere. It was quickly named the Great Dark Spot. It was roughly the size of Earth. Winds along its edges were measured at up to 2,400 kilometers per hour, the strongest ever recorded in the solar system. Scientists watching the data come in described the experience as being extraordinary. Every day they said, "You were seeing something no human had ever seen before." But here's where Neptune started showing its character. When Hubble Space Telescope was turned toward Neptune in 1994, just 5 years after Voyager's visit, the Great Dark Spot was gone. Completely. No trace. Jupiter's Great Red Spot has been raging for centuries. Neptune's storm of equivalent size had simply vanished in less than a decade. Hubble has since watched a succession of dark vortices appear across Neptune's surface, wander across the planet, and then fade away. A new large storm was observed in 2018 and has been tracked ever since, slowly shrinking as it drifts toward the equator. The way these storms are thought to work involves bands in the atmosphere moving at different speeds. Where two bands meet, the friction between them can seed a vortex. That vortex can sustain itself for years, as long as it stays within a certain atmospheric region. But once it migrates out of that zone, it loses its energy source and dissipates. The process makes sense in theory, but storms the size of entire planets appearing and vanishing on timescales of years, that is something no other planet in our solar system does. Now here is one of Neptune's most genuinely puzzling characteristics. You would reasonably expect that Neptune, being the furthest planet from the Sun and receiving the least solar energy, would be the coldest planet in the solar system. It is not. That distinction belongs to Uranus, despite Uranus being significantly closer to the Sun. Neptune actually radiates more heat into space than it receives from the Sun. Something inside the planet is generating additional energy. The most widely accepted explanation is that Neptune still retains significant heat from the period of its formation billions of years ago. Primordial warmth, slowly leaking outward through the planet's layers over geological time. Uranus, by contrast, radiates almost no excess heat. One leading theory holds that Uranus was struck by a large object very early in the solar system's history, something roughly Earth-sized. An impact so catastrophic that it tilted the planet onto its extreme axial angle and disrupted the flow of heat from its core. Uranus has been slowly cooling ever since. Neptune appears to have avoided a similar fate, and so its internal warmth survived. That internal heat is now thought to be a significant driver of Neptune's extreme weather. More energy rising from below means more convection, more turbulence in the atmosphere above. The Sun, this far out, is barely a factor. Neptune receives roughly 1,000 times less sunlight than Earth does. The engine powering its storms is not above it, it is beneath it. And deep inside Neptune, things get stranger still. Beneath the atmosphere lies a mantle of water, methane, and ammonia. Not in solid or gaseous form, but compressed into an exotic state that conducts heat and electricity in ways that do not fit our ordinary categories of matter. This layer is sometimes called a water-ammonia ocean, though that description only captures part of how unusual it actually is. Even deeper, where the mantle meets the core, the pressure is estimated to be around 7 million times the atmospheric pressure at Earth's surface. Under conditions like that, something remarkable may be happening. The carbon in methane molecules is theorized to break free under that unimaginable pressure and crystallize into diamond. Not diamonds as we typically picture them, perhaps a fluid layer of liquid carbon with solid diamond structures floating within it, and a constant rain of diamond crystals falling slowly through the mantle toward the core. Laboratory experiments in recent years have begun to confirm that this process is physically possible at those pressures. Neptune may contain more diamonds by mass than any other object in the solar system, falling silently through the dark interior of a planet 4.5 billion kilometers away. Neptune also has rings. They were suspected before Voyager 2's arrival, but could not be confirmed from Earth-based observation. Voyager settled the question definitively. Neptune has at least 5 distinct rings, all named after figures connected to the planet's discovery and study. The innermost is the Galley ring, faint and broad. Moving outward, the Leverrier ring is brighter but narrower. The Lassell and Arago rings sit in between. And the outermost, the Adams ring, is the most studied of the 5. Triton does the opposite. It orbits backward, retrograde, and at a sharp angle of roughly 130 degrees to Neptune's equatorial plane. This is not what a moon that formed alongside Neptune would do. This is the signature of a captured object, something that did not form here and was not supposed to be here. The leading theory is that Triton was once a dwarf planet in the Kuiper Belt, the region of icy bodies that exists beyond the orbit of Neptune. It was orbiting the Sun independently, possibly in a binary pair with a smaller companion, when a gravitational encounter with Neptune pulled it inward. One possible mechanism is that as Neptune's gravity separated the pair, the smaller companion was flung away into space while Triton lost enough momentum to be captured into orbit. Over billions of years since then, gravitational forces have slowly circularized Triton's orbit until it is now almost perfectly round, while still remaining retrograde. The consequence of this retrograde orbit is gradual but ultimately dramatic. Triton is slowly spiraling inward. In approximately 3-6 billion years, it will cross the Roche limit, the boundary inside which tidal forces overcome the structural integrity of a body. Triton will be torn apart. Neptune will gain a spectacular new ring system, potentially rivaling Saturn's rings in scale and density, an entire moon broken apart and stretched into a ring by gravity, the solar system's most dramatic future event, playing out in slow motion. But Triton is not simply waiting passively for its end. Its surface is one of the coldest places ever measured in the solar system, around minus 235 degrees Celsius. Beneath a thin atmosphere of nitrogen, the surface is covered in nitrogen and methane ices. And yet, when Voyager 2 flew past, it observed geysers, plumes erupting from the surface, reaching heights of 8 kilometers, sending dark material hundreds of kilometers downwind before it settled back to the ice. These plumes are thought to be driven by a solid greenhouse effect. Sunlight, even as dim and distant as it is this far from the sun, passes through the transparent surface ice and is absorbed by the darker organic material just beneath it. Heat builds in that pocket until a burst of sublimating gas ruptures through the surface in a dark, streaking plume. It is one of the most alien forms of geological activity ever observed anywhere in the solar system. And beneath the surface, there may be something even more significant. Triton's density and its rocky, metallic interior suggest that radioactive decay within its core could be generating enough heat to sustain a liquid water ocean, sitting between the rocky interior and the ice shell above. If that ocean exists, Triton joins Europa around Jupiter, Enceladus around Saturn, and Titan also around Saturn, as a world with the potential conditions for life as we understand it. An ocean, liquid water, beneath the ice, on a captured dwarf planet at the outer edge of the solar system, orbiting backward, slowly falling to its end. And now we reach the part of the story that brought everyone's attention back to Neptune in 2025. For decades after Voyager 2's visit, Neptune sat at the edge of our knowledge, studied from a distance, observed by Hubble, slowly revealing small pieces of information. Then, the James Webb Space Telescope came online. Webb is a fundamentally different kind of observatory. It operates primarily in the infrared, detecting heat and wavelengths of light that are invisible to human eyes and to most previous telescopes. It is designed to see things that were simply out of reach before. When Webb turned toward Neptune, it was looking for things Hubble and Voyager could not clearly capture. What it found was remarkable. In March of 2025, Webb released images showing Neptune's auroras, faint but unmistakable, ribbons of light shimmering across the planet's atmosphere. Auroras on Neptune are not a new concept. We knew they existed in principle. Aurora happen when charged particles get trapped by a planet's magnetic field and interact with the atmosphere. Earth has them at the poles, Jupiter has them, Saturn has them. Neptunes were expected to exist, but they had never been directly imaged with this kind of clarity before. But there is a significant difference between what we expected and what Webb showed us. Neptune's magnetic field is unusual. Unlike Earth, where the magnetic axis is reasonably close to the rotational axis, Neptune's magnetic field is tilted 47 degrees relative to its rotational axis and is also significantly offset from the planet's center. This means the magnetic field is not centered on the planet and does not align with the poles the way you would intuitively expect. The result is that auroral activity on Neptune does not concentrate at the poles. It appears at the mid-latitudes, across the wider midsection of the planet. Webb's near-infrared instruments captured exactly this, glowing light arcing across the planet's mid-latitudes, in a pattern that reflects the bizarre geometry of Neptune's magnetic field. No telescope had managed to capture this directly before. Webb did it clearly. These are known as SR arcs, stable auroral red arcs. Earth has them too, but they are invisible to human eyes and so faint you need specialized instruments to detect them. On Neptune, Webb's sensitivity was powerful enough to image them directly, and they were stretching across the whole planet. But the auroras were only one part of what Webb found. At the same time it was imaging the auroras, Webb was also measuring temperatures in Neptune's upper atmosphere. And what it found there created a very different kind of conversation among scientists. When Voyager 2 visited Neptune in 1989, it measured temperatures in the planet's thermosphere, the upper layer of the atmosphere. Those readings gave scientists a baseline, a reference point for Neptune's atmospheric state. Over the decades since then, Hubble and other telescopes have continued monitoring Neptune when possible, building up a longer-term picture of how the planet changes. What Webb's data showed is that Neptune's upper atmosphere has dramatically cooled since 1989. The thermosphere temperature had dropped by hundreds of degrees, falling to nearly half of what Voyager 2 recorded just a few decades ago. This is an enormous change. Temperature shifts on planetary scales usually happen over geological timescales, millions or billions of years, not decades. For Neptune's thermosphere to lose that much heat in the roughly 35 years between Voyager's visit and Webb's observations is, by the standards of planetary science, almost shockingly fast. And right now, no one has a clear explanation for it. Several possibilities are being discussed. One is that this is related to long-term seasonal cycles. Neptune takes 165 Earth years to complete one orbit around the Sun, one full Neptunian year. Its axial tilt of 28 degrees means it does have seasons, but each season lasts about 40 Earth years. Since its discovery in 1846, we have only seen Neptune complete one full orbit. We are still in the very early stages of understanding how its seasons affect its atmosphere over a full cycle. The temperature drop could be part of a long seasonal pattern that we simply have not had enough time to observe from start to finish. Another possibility involves changes in the internal activity of the planet. If the heat rising from Neptune's interior has changed in some way, that could affect the temperature distribution throughout the atmosphere. But what would cause that change is not clear. A third possibility is that there is a connection between the temperature drop and the auroras. Cold temperatures in the upper atmosphere reduce the conductivity of the gases there, which might help explain why Neptune's auroras have historically been so faint and so difficult to detect. If the thermosphere has been cooling over recent decades, that cooling itself might be contributing to the dimness of the auroras. And conversely, the fact that Webb could image them at all might partly be due to how much things have changed since 1989. We know it has storms that dwarf our entire world and then quietly vanish. We know it almost certainly holds diamond rain in its interior. We know it has a moon that was stolen from the outer solar system and is slowly falling toward a catastrophic end that will reshape the entire planetary system in a few billion years. We know that Moon may have a liquid ocean beneath its frozen surface. We know Neptune's rings clump in ways that ring systems are not supposed to clump, and we do not fully understand why. We know its winds blow in the opposite direction to its rotation, and we do not fully understand that either. And now we know that its upper atmosphere has dramatically cooled in a way nobody predicted, while lights glow in places they are not supposed to appear. For every piece of information we gather, Neptune seems to offer 3 new questions in return. There are currently no confirmed missions to return to Neptune. Budget constraints and competing priorities have kept the outer solar system at a lower rank on the mission list. The window for another efficient gravity-assist trajectory like the one Voyager 2 used has long since closed. China has proposed a Neptune mission with a potential launch window around 2033, which would be a significant step forward if it proceeds. But as of now, Neptune remains largely unexplored. One visit, decades of watching from a distance, and a handful of stunning images from Webb that changed how we see it, while simultaneously showing us how much we do not understand. We live in a time when we have mapped Mars in extraordinary detail, when rovers drive around on another planet's surface and send back photographs every day, when telescopes can look at galaxies billions of light years away and analyze the chemistry of their stars. And yet, the last planet in our own solar system, in our own neighborhood, remains almost entirely unknown. Neptune does not make itself easy to reach. It sits at the edge of everything we consider nearby. Vast and cold and ancient, still radiating heat from the violence of its formation, long before life ever appeared on Earth. It holds storms and diamonds and captured moons with buried oceans, all wrapped in a blue atmosphere moving faster than sound and in the wrong direction. And after everything we have learned, after Voyager, after Hubble, after Webb, it still feels like we are only just beginning.